Today we are taking a look at another specific type of problem that is on the free response section of the AP exam. We are looking at problems where they give us velocity. Usually they give us an equation for velocity, and then it'll ask us questions, either about the position of the particle, about its total distance traveled, its acceleration, things like that. So the most common problems are we are asked to find acceleration. To find acceleration, we are going to take the derivative of velocity. These problems are typically calculator problems. Because they're calculator problems, you could graph velocity and then just use the dy dx function on your calculator. Often we will be asked to find position. If we are looking for position, we need to know how far did it move. So the overall displacement starting with the velocity to get to a position, we are going to integrate v of t dt. Starting at time, whatever the time starts with, A, and ending at our ending time B. That gives us displacement. So that tells us if it started here, we would then be able to know maybe it moved way out here and came back. That would give us this distance right here. If I need position, we are going to find the displacement and then add in its initial position. So if it started at 20 and I know it moved up by 12, I'm going to find this displacement is 12 and then add the 20 that it started with to get a total position of 32. And then the other most common problem that is on there is if it asks us for the total distance traveled. Total distance traveled. I'm given a velocity and I need a distance. Distance, that sounds like the integral position of velocity. So we are going to integrate. We're going to integrate from A to B. The problem is if I integrate from A to B of just velocity, if this particle started here and moves up maybe 30 units, let's get rid of that 20 also. So it moved up 30 and then it moved back 18. If I integrate from A to B, that's going to count this as positive 30, this is negative 18, and it's then going to spit out 12. I want total distance traveled, I want 30 plus 18. So basically any way it moves, whether it moves in the positive direction or if it moves in the negative direction, I want to count that as a positive distance. And we can do that by taking the absolute value of velocity. Absolute value is going to take anything and make it positive. Total distance traveled is the integral from A to B of the absolute value of v of t dt. One other thing I want to mention, it'll also often ask if the particle is speeding up or slowing down. We have talked about this before. To tell if it's speeding up or slowing down, speeding up, we have velocity and acceleration have the same sign, either both positive or both negative. If it is slowing down, velocity and acceleration have opposite signs. One is positive, one is negative. It does not matter which one is which. So let's take a look at a few of these AP problems that deal with these types of problems where we are given the velocity. So number one, or I guess it's number two, says a particle P is moving along the x-axis. The velocity of particle P is given by that equation. So equation is given. This is an equation for the velocity of particle P. It also tells us at time 0, the particle P is at a position of 5. It gives us the same information for a second particle Q, different equation for velocity, different starting position. So this is a calculator problem. It certainly would be. So let's go ahead on our graphing calculator. Let's graph y equals the two equations that are given. So y1 is equal to sine of t to the 1.5 power. Double check to make sure you are in radians mode. Make sure your parentheses in the right place. And v sub q of t is equal to the quantity t minus 1.8 times 1.25 tx. And I'm going to zoom standard. Looks like our times go from 0 to pi. So let's change our window. X is going to start at 0. I'm going to go negative 0.1 so I can see the axis. And we are ending at pi. And as it graphs it there, it looks like it's all scrunched up around the x-axis. So we might want to change our y min and y max as well, so we have a little bit better graph. I'm going to do that. Let's go -4 and +4. I think should do it. So that looks a little better. If you want to go -2 and +2, that might give you an even better graph. So part A asks us to find the positions of particles P and Q at time t equals 1. So particle P, the work that you would be required to show is show that you are integrating. We are integrating v sub P of t dt. We are starting at time 0. We are starting at time 0 because I know where it is at time 0. And ending at time 1 because I'm looking for where it is at time 1. So the integral from 0 to 1 of v sub p of t dt. We want to make sure it graphs, or we integrate the v sub p equation. So let's turn off our y2 equation. And then we can integrate. Second trace. Number 7, starting at time 0 and ending at time 1. Remember, this is not going to give us the position. This is giving us the displacement, how far it is from where it started. Wherever it started, it then moved to the right 0.371 units. So this is 0.371. It's asking for the position. We need to consider where it started, so we're just going to add on the 5 where it started for a total position of 5.371. To find the position of particle Q, we do the same thing, but we use the v sub q equation. So the integral of v sub q of t dt, starting at time 0, that's where we know where it is. Ending at time 1, that's where we want to know where is it. Turn your y1 graph off and your y2 graph on. Notice the velocity is negative from 0 to 1. That means it's moving to the left on that interval. So when we integrate from 0 to 1, we should get a negative value this time. It moved to the left 1.436. That is its displacement. To find where it is, we add 10 because it started at a position of 10. On your calculator, you can just push +10. The previous answer it takes will be that integral that we just found, 8.564. Part B wants to know, are the particles P and Q moving toward or away from each other at time 1? Are particles P and Q moving toward each other or away from each other at time t equals 1? So at this point in time, if I draw my number line here, that's not a good horizontal line, but point P is right here at 5.371. And point Q is over here at 8.564. So Q is to the right of P. We need to know which way is P moving and which way is Q moving. So I need to know the velocity of P at time 1 and the velocity of point Q at time 1. You can get that either by plugging 1 into the equation, or I'm going to turn both graphs on. If we look at the table, because we graphed velocity, we should be able to find the velocity of point P to be 0.841, and the velocity of Q was -1. So that tells us that P is moving to the right because it has a positive velocity, and Q is moving to the left because it has a negative velocity. Therefore, particles P and Q are moving toward each other. As far as your reasoning, I would say Q is to the right of P and moving left. You have proven that it's moving left by showing what its velocity is. P is moving right. Part C wants us to find the acceleration of particle Q at time 1. Find the acceleration of Q at time 1, and then is the speed increasing or decreasing? Is the speed increasing or decreasing? That wants to know, is it speeding up or slowing down? So we need the acceleration of Q at time 1. So acceleration of point Q at time 1. Acceleration is the derivative of velocity. Point Q was my y2, so let's turn off y1. We're just working with y2. We want the derivative of this at 1. So derivative, we go second trace. Number 6 is derivative. And it wants to know at what x value do you want the derivative. We want the derivative at 1. Our acceleration is 1.027. 1.027. Just because I have a positive acceleration does not mean speeding up. To tell speeding up or slowing down, we look at the velocity. So it's moving to the left because velocity was negative. Acceleration is positive, which means it's being pushed back to the right. It's accelerating to the right. So it will continue moving left, but it's going to be slowing down. So speed is decreasing. Explain your reasoning. I would state acceleration and velocity have opposite signs. At t equals 1. And we showed that they have opposite signs here. Part D asks us to find the total distance traveled by particle P over the interval from 0 to pi. Find the total distance traveled by particle P. So I'm looking for a distance. I'm given velocity. Distance from velocity tells us we need to integrate. It gives us our time interval here, 0 to pi. Total distance traveled, whether I'm moving in the positive or negative direction, I'm going to count that as positive distance. So we are going to integrate the absolute value of v of t dt. Probably should show that it's v sub p of t that we are integrating. On all your integrals, make sure you have your dt. That's important. In order to find the answer here, let's go down to y3. We want the absolute value of y1. So absolute value on your calculator, you go to math, scroll over one time to number, and absolute value is number 1. We want the absolute value of y1. To get y1, we push alpha trace. And then I can put in y1. We only want to graph y3, so we are going to turn off y2, make sure y1 is off, calculate the integral, and we will start our integral at 0 and end it at pi. Notice previously when I just graphed y1, it came down here. If I had integrated, it would have counted this as negative area. We don't want that. We want all of it to be positive. So starting at 0 and ending at pi. With total distance traveled, we do not care where it started. We just want to know how far did it move. So we are not adding in the initial condition. It's just 1.932. If we're looking for a position, where is it? We care where it started. How far did it move? What's its total distance traveled? It doesn't matter where it started. 1.932 is our answer. Let's try another one here. Again, a number 2. The fact that it's number 2, we know it's a calculator problem. It gives us an equation for velocity. It gives us the time interval that we are working with, and it tells us its position at time 0. It isn't necessarily always going to be time 0. It usually is, but it might say its position at time 1 is whatever. Part A, what's the acceleration? Again, it's a calculator problem. Let's go ahead and clear out all of our equations and graph the velocity equation that's given. Sine of x squared. We should probably make our window to try to mirror the graph that's given. So on my window, my x, I'm going to start at 0. Again, I'm going negative 0.1. X max is square root of 5 pi. And y's look like go from negative 1 to 1. So we've got the given graph. Part A, find the acceleration at time 3. Acceleration at 3 would be equal to the derivative of velocity at time 3. We want the derivative, second trace, number 6, at time 3, enter, negative 0.567. Nope, negative 5.467. Part B asks us to find the total distance traveled from time 0 to time 3. Total distance traveled is the integral of the absolute value of v of t dt. Starting at time 0 and ending at time 3. So y2, we are graphing absolute value of y1, making sure that y2 is the equation we are graphing, and we are integrating from 0 to 3. $1.705. Part C, find the position of the particle at time 3. Position, we need to consider where it started. It started at 5. And how far it moved and in which direction. Its displacement we get by integrating from its starting time 0 to its ending time 3 of v of t dt. And this is where if it had told us t equals 1 here, this would be a 1 down at the bottom. We do not want to graph the absolute value this time. So y1 graph on, y2 graph off, calculate the integral from 0 to 3. Uh, 0.774 plus the 5 gives us 5.774. Part D asks us to find the time at which the particle is farthest to the right. When is the particle farthest to the right? Farthest to the right. Basically, it wants to know what is its maximum position. When is its position the greatest? Well, to find a maximum, we take the derivative. Derivative of position is velocity. And we set it equal to 0. So we want the zeros. Well, I've got a lot of zeros here. We want to consider, do I need all these zeros, or are there some of them that can't possibly be correct? So notice we're starting at time 0. At time 0, it was at 5. So here's 5 at time 0. After time 0, it is moving to the right. And it is moving to the right because its velocity is positive. It's above the x-axis. And it keeps moving to the right. And here it's still moving to the right because velocity is positive until this point right here. At that point, now its velocity is negative. So it stops, it moved to the right, and it stops, and now it turns around and moves to the left. Notice that could be a point where it's furthest to the right. If it never gets back to that point or further, that would be our maximum. Notice this point right here. It's moving left, moving left, moving left, moving left, 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 turns around and moves to the right. Moves left. Maybe it goes past this or not. We'd have to do some analysis to do that, but then at some point it turns and moves back to the right. Notice because that is a relative minimum, it moves from left to right. That is not going to be a point where it's furthest to the right. Think about where the other ones might be. This point right here, and this point right here. So those are the 3 values we're looking for. That last one is pretty clearly square root of 5 pi. Let's find the other 2. The other 2 we can get on our graphing calculator. We want to calculate the 0. Oh, I can't read my tick marks. Clear that graph and then regraph it, I guess. So this point here is between 1 and 2. Calculate that 0 between 1 and 2. 1.772. Not that one, we want this one. Looks like it's just past 2. I'm going to calculate my 0 from 0 to square root of 5 pi. I'm going to use the whole interval. And when it tells me to guess, I'm going to guess, I'm sorry, that's 3. T equals 3. And it's very close to 3, not quite. 3.070. And we had that last point. Those are the points that might be the maximum position. To show which one is the maximum position, we want to get the position of each of those. So T and position. at time 1.772 to get its position, we would integrate from 0 to 1.772. And its position is 0.895 plus 5, because that's where it started. I don't know what happened there. Find the position at 3.070. Start at 0, end at 3.070 plus 5 gives me 5.788. And at square root of 5 pi, we would do the same thing, but change the end value. Plus 5 gives us 5.752. Make sure you answer the question. Find the time at which the particle is moving farthest to the left. That time would be 1.772. That is the greatest position.